Name is Mark Miller. I've been a consulting structural engineer in the Denver area for about 37 years. And the last 15 years or so I've been occasionally doing horizontal lifeline engineering. I was asked to come and explain how I do that. Let's see. I'm also not very experienced with PowerPoint presentations. Okay, you're probably all familiar with the typical horizontal lifeline. It's a cable suspended between 2 points. We call the distance between the points the span, and you have an initial sag, or you should have an initial sag in there. A cable hanging under its own weight forms what's called a catenary curve. It's not a circular curve, it's a parabolic curve, and it's difficult to compute the exact length. There's a big complicated formula to do that, but we don't like to do that very much. We need to start with the geometry of the system, and then we can calculate the forces involved. We need to ensure that the forces don't exceed half the cable strength in order to comply with OSHA's requirement for 2-to-1 safety factor. Okay, to avoid calculating that length of that parabolic curve, we just pull the cable down until it's almost straight, and then we can do the geometry in a much more simple way. There's still a little bit of curvature there, but we can ignore that because it's conservative to have a little extra cable length. The calculation of the length is according to the Pythagorean theorem, which says that the long side C equals the square root of the other two sides squared and added together. So typically those are called A, B, and C, and the formula is A squared plus B squared equals C squared. And then the calculation of the forces follows the same proportions as that. Okay, so per OSHA, did this stop? No. Per OSHA, to maintain a 2-time safety factor, tension has to be less than half the ultimate breaking strength of the rope. The ultimate strength is calculated by taking 80% of the strength that the cable is rated for, because with clamps and hardware, it crushes the cable a little bit. You're going around corners, so there's a strength reduction. So for a typical 3/8 inch rope, that's rated at 14.4 kips, 14.4 thousand pounds, and 80% of that gives you 11,520 pounds. Dividing that by 2, you have a usable strength, basically, of 5,760 pounds. So you have to maintain or ensure that the cable tension is that or less in order to maintain the 2-to-1 safety factor. For simplicity, I'm going to start with just a simple single span and a one-man tie-off. You can get much more complicated than that, and we'll get into that a little bit later. Okay, the forces are resolved into a horizontal and vertical component. Those are, in engineer talk, referred to as vectors, and the two forces horizontally and vertically add up to the diagonal tension. And those forces follow the same Pythagorean theorem, where the square of the vertical plus the square of the horizontal equals the square of the diagonal. We're going to take that triangle and make it into 2 triangles and look at each half of the triangle separately. The typical lanyard for one-man use is going to tear out in a fall and exert a force of 900 pounds on the system. So each half of this system is going to carry 450 pounds of vertical force. Depending on the angle, then that determines what the tension is and what the horizontal force is. Okay, the Pythagorean theorem deals with that, the relationship of the sides of the triangle. A typical numerical example is a 3-4-5 triangle there on the center up above, where the long side is called the hypotenuse. That would be 5. The vertical side is 3, and the horizontal side is 4. This is one of the few triangles that works out numerically with whole numbers. And you can see that if you take the A side, 3, square that, 3 squared is 9. You add that to the B side, 4, square that, that's 16. That adds up to 25. Square root of 25 is 5. That's the other side. The only other triangle that really does that is 12, 13, and 5. That works out in whole numbers, integers. The Pythagorean theorem applies only to right triangles, that is with a square corner, right angle. But you can always divide a triangle into multiple right triangles. So any triangular system can be resolved into right triangles that you can then apply the Pythagorean theorem to. The sum of the internal angles of a triangle always adds up to 180 degrees. Like the isosceles triangle on the left there is 180 degrees. They're all 60-degree corners. If you divide that in half and make it a right triangle, you have one corner that's 90 degrees, and the other two angles add up to 90 degrees also. Okay, there's just a couple of examples of the Pythagorean theorem numbers. They can be lengths or they can be forces. As long as the units are the same, whether they're inches, feet, pounds, or thousands of pounds, the numbers will still work out according to the Pythagorean theorem. Now I want to just say a little bit about the trig functions of sine, cosine, and tangent, because they're so useful in calculating this stuff. If you take that same 3-4-5 triangle and you divide all three sides by the same number, the ratios stay the same. So we want to make the hypotenuse 1. So dividing the 5 side by 5 gives you 1. You divide the other two sides by 5 and you get what's called the sine. The sine is the side opposite the angle, and the cosine is the side that's adjacent to the angle. So those ratios are 0.6 for the sine and 0.8 for the cosine. Those are related to the angle, and those are unique to that angle. The tangent is the sine divided by the cosine, or in this case it would be 0.6 divided by 0.8, equaling 0.75. So those relationships hold and they're linked to the angle. Now to use that in calculating cable tension, in the upper left there you have the basic system with the person that we're saving hanging on his 900-pound lanyard. We're going to resolve that into two components, each carrying 450 pounds. That's the lower left. And if you move to the upper right there, the forces are calculated by setting the vertical leg at 450 pounds. If you take that 450 pounds and divide it by the sine of the angle, that's the, where's that? Okay, right where it says T equals 450 over the sine alpha. 450 divided by 0.6, the sine gives you 750 pounds. So with that angle, if you have 450 pounds, the tension in the cable is 750 pounds. Then you can take that number and multiply it times the cosine, the 0.8 on the horizontal side. That will give you the horizontal force. That's the F sub h, 750 times the cosine. That gives you 600 pounds. So this is telling us that there's 600 pounds of horizontal force for the 450 pounds of vertical force, and the tension in the cable is 750 pounds. Again, you can check that by squaring the two sides, adding them together, and making sure that they add up to the square of 750. And so that checks. Now, in the lower right-hand corner is another alternate method that some people use, where you just make a multiplier out of that, what is actually the sine. If you take the tangent, the long side, which is 5, divide it by the vertical side, 3, you get 0.6. Or if you take the 1 over that number, you get the multiplier of 1.667. And if you then multiply the 450 times that multiplier, you again get 750 pounds for the cable tension. To me, that's a more awkward way of doing it, but it might look a little simpler. Okay, this is just an explanation of how we're going to do the actual calculation. That was the theory. We'll apply it to a real example here. First, we find the geometry from the two known sides, from the horizontal half the span and the vertical length of the initial sag. We can calculate the third side, or the length of the diagonal of that cable. And from those, you can then get the angle. Once you know the angle, then you can calculate the forces. So we next want to calculate we apply the 450 pounds and calculate the forces in those legs, and we'll find that that's going to be enough to stretch the cable, which is one reason you always want to use a new cable for a horizontal lifeline, because we depend on the stretch. That's going to be about 1.5%. As the cable nears its ultimate strength, it's going to stretch 1.5%, which makes the diagonal longer, which gives you more sag and reduces the force. So you calculate the initial forces and then put the stretch in. And this produces a new angle, and then you calculate the final forces, apply the 450 pounds to the new configuration and check the final tension. The final tension should be less than the 5.76 kips. Hope you can see that adequately. This is an example with a 60-foot span, which is a bit long, maybe longer than you really want to use, but it's just an example. And we're only going to start with a 6-inch initial sag, which is pretty minimal. Now, to have the units work out, you have to have the sag in feet if the span's in feet. So first, we assume that the initial sag is going to be 6 inches or half a foot. And then we can find the length of that cable on the diagonal. The initial length is the square root of 30 squared plus 0.5 squared. That comes out to 30.0042 feet. Now that's only 51 thousandths of an inch longer than the cable was initially, because it's so long and such a flat angle. If you use that angle then of 0.95 degrees, that tells you that with a 450-pound vertical force, the cable tension is going to be 27,000 pounds. That would be enough to break the cable, most likely, except that that's going to cause the cable to stretch. So if you take 1.5% of that 30.0042 feet, You find that's 0.45 feet, which is about 5 3/8 of an inch. That's how much the cable will elongate. So you go back and add that to the initial cable length, step 5 here, and you find a new length, which ends up being 30.4543 feet. Okay, from that, then you take the cosine, you find the cosine, the number would be the 30 feet divided by the diagonal length, and take the inverse of that, the inverse cosine of that, you find that the new angle is going to be almost 10 degrees, 9.91 degrees. If you then calculate the forces based on that angle, 450 pounds, the tension comes out to 2,615 pounds, which is less than the 5,000, so that works. If you usually are interested in how far the sag goes down, because you got to be sure the guy isn't going to hit the ground or a lower deck or something. So then you can go back, use that angle times the diagonal length to find B. That would be step 7 here. B in this case would be 5.24 feet. Okay. This shows you the calculation of tension at various angles, which is hopefully will give you an indication of how quickly the tension goes up at flatter angles. If you start at the bottom there, the angle is 63 degrees. The tension is only 500 pounds with 450 pounds of vertical. The vertical scale is the same on all of these. The next one is 45 degrees. The tension is 636 pounds. Next is 20 degrees, and you're up to 1,200 pounds. 13 degrees, you're up to 2,000 pounds. 9.5 degrees, 2,740 pounds. 7 degrees, you're at 3,480 pounds. And scale-wise, the 3 degrees there wouldn't fit on the page, but that goes to 8,600. 1 or 2 degrees, 12,000. 1 degree, 25,000 pounds. And a half a degree, you're up to 51,000 pounds of tension. That would be plenty to break the cable. So that's why you don't want to ever tie off to a taut cable like a guardrail cable that's stretched tight where there's no angle. The force would actually approach infinity as the angle gets flatter just from pulling sideways on the cable. Okay, this is a little demonstration of why we start at the center, because not everybody's going to fall at the center of the cable. But we do the calculations based on the center because of this. If you start with an off-center fall, let's assume we're 8 feet from one end and on a 30-foot total span, 8 feet from one end, 22 feet from the other end. You end up, I assumed a 4-foot sag here just as a starting point. You end up with 2 different triangles. So the 450 pounds doesn't apply because the triangles aren't equal, so the forces aren't equal. It's a little complicated to calculate what's going on. The equations there show you how you do it. The tension in the cable is the same in both legs of the cable, because you can't have more tension on one side than the other because it equalizes. So the vertical leg there of 4 feet, that would be the sine of the angle. And from the 4 feet and 8 feet and 4 feet and 22 feet, you can calculate the angles. If you divide the 4 by 22, for example, take the inverse tangent of that tells you the angle. And same thing for the other side. So it's 26 degrees on the left and 10 degrees on the right. The numbers below here in the little diagram are showing how the forces resolve. For the steeper angle with 900 pounds, it gets divided into 643 on the left and 257 on the right. They have to total 900 pounds. And then you can solve for the cable tension. You get 1,437 pounds of cable tension. And the horizontal forces down at the bottom there, the left is 1285, the right is 1414. Those aren't balanced. So there's 129 pounds of force pushing the load towards the center, which makes sense. If you fall off center on a cable, you're going to slide towards the center of the cable. Okay, remember that tension there, 1437. And we go to the next slide. Now here we've moved over a little bit. We're 12 feet in and 18 feet from the right. Do the same thing. You resolve the two triangles into their different angles. And the forces come out at the bottom there, 533 pounds on the left, 367 pounds on the right. Those again add up to the 900 pounds, but the cable tension has gone up from 1437, it's now 1550. The horizontal forces are not equal, but they're closer to being equal. There's only a 50-pound difference now. So as you get closer to the center of the span, the force that is tending to push the load to the center of the span becomes less. And when you finally get to the center of the span, it resolves into a stable system. So here's the numbers for the center of that system. It's the same system with the load at the center, and the tension from this calculation is 1,575 pounds. So the closer you get to the center, the higher the force is. So basically we don't even bother looking at the forces elsewhere. We always just look at the forces involved in falling at the center. This is just the mathematics involved in calculating the off-center triangles, because you have three unknowns there, so it's kind of an exercise in algebra. You have to write, if you have three unknowns, you have to write three independent equations for those unknowns, and then start adding them up, and you solve for the unknown quantities. So if anyone has questions about that, we can talk about that later. Okay, this is probably a more realistic example where you have multiple spans in your lifeline. This helps, it's better than just a system where you're tied off tight at both ends, because you have a longer cable where the cable is tied off at the far ends but passes through holes in the steel or washers welded to the steel or something, or safety posts. Because with this system, then you can take advantage of the entire length of the cable for stretch. So your longest span is going to be the worst case, but the span is considered to be between two support points. So you have the same system, but it resolves into just the one span, and you get the advantage of the stretch of the entire length of the cable. Let's see. Oh, now this also will apply to like a system where your lifeline is laying on a deck or is horizontal. There, the sag, you want to pull the sag sideways to measure it. And if you're over a system of joists or something, it's the same thing. You have a very long cable and a very short span, so it's very advantageous. You still need to have some sag or slack in that cable to give you an initial starting point that's not tight. Now for multiple man falls, it's just a matter of putting more force on. Instead of the single 900 pounds, I usually put on twice that for a two-man fall, twice 900 pounds. There's an engineer named Andrew Solonsky that's published data that says you don't have to double that force. You can, he's determined that it's somewhere between 1.2 to 1.4 times the single force for a two-man fall. To me, that doesn't make a lot of intuitive sense. He claims he's measured it, I guess. But I generally use the factor of 2 anyway, just to be conservative. That kind of a system may need more sag initially or may need a heavier cable in some cases. I don't know if that shows up very well, but this is a generic sag table that we developed for Miller Safety. This is a basic worst case scenario with rigid ends where there's no give at either end. It's a single span, and it tells you what the sag should be for a two-man tie-off where you want two people tied to the single cable. And I thought they were going to publish these slides to present to you, but if anybody wants these, give me a card or something and I'll send them to you. So I think basically that concludes what I was going to say. Now we probably have some questions. Was everyone totally overwhelmed? Yes, sir. Yes, the anchor point, well, generally the anchor point is a piece of structural steel or sometimes an anchor bolted to concrete. You do need a solid anchor point at one end. I mean, at both ends.
But I'm saying you're engineered anchor points. This is an engineered design, so your anchor point would be your first.
Well, yes, but if you have a structural steel column, a 5,000-pound pull on that is basically nothing.
You don't have a structural column, say you're going to masonry walls. So that's the only things you've really got. You're constructing steel on.
Okay, you can design. We have some typical designs for anchoring a ring or an eye bolt to a masonry wall, or.
That would be something that, like you said, that they would be able to supply that calculations.
Yes, we provide, for a specific system where people have specific spans and end anchorages, we can design a system and write a letter and give you some details showing the anchorages. Mm-hmm.
Is this presentation on the flash drive we received?
Yeah, it's on the flash drive.
Okay. Okay, any other questions? There's a lot of possible variations. Everybody's got a different setup. I know there are a lot of post systems that have Preferred Safety has one where you have a piece of a metal plate that's designed to bend over. So with that system, you can elevate the cable more and get it a little tighter, because when there is a fall, then those plates, they're sacrificial. They will bend over and give you more slack to keep the tension forces within the allowable range. I guess there's also some systems, kind of like the lanyards, where you have chains that are tied together with wires that tear out. There's various ways of getting a tighter cable. But if you don't have something in the system like that, you don't ever want to tie off to a taut cable because you can break it. Yes?
Have you ever done drop tests to compare the numbers with your engineering?
Mm-hmm. Yeah, you have to put a dynamometer in the system, and if you film it at high speed, you can see a lot of whipping in the cable. I mean, it's not just it doesn't go like a static test. There's a lot of whipping and kind of waves that reflect back and forth and things that bang around. So the actual forces are probably much less than the calculated forces.
Yeah, your max numbers.
Yeah.
The ones that you
Right.
max here. Yeah.
But, we want to be conservative and safe, so we basically want to calculate the worst possible case, and in reality it's going to be less than that probably. Also, the duration of a fall is extremely short. It's a kind of a shock load that it's over, and then you just have the weight of the person hanging there. I don't have any calculations for that, but it's just a matter of, it's the same calculation, but instead of using the 900 pounds, you double it or triple it if there's 3 guys tied off. You generally end up needing to start with more sag or a bigger cable. Some systems will go to a 1/2-inch cable. So, anything else? Okay, well, I guess that's it then.